Good. So what we want to do today is prove lower bounds for arithmetic circuits. Okay, so that's the goal. Well, so remember, the big question is, of course, separating VP from VNP. We will not do that, but we'll show, the techniques that we know today, prove some unconditional lower bounds for general circuits, but most of what we'll prove will be lower bounds for restricted classes of circuits. But as a sanity check, one should first verify that counting arguments give lower bounds, and that there are lower bounds, that we can prove lower bounds. So, okay. So what I want to do is, what are counting arguments is basically showing that a generic polynomial or a random polynomial is how to compute. So when you speak about Boolean circuits, that's fairly easy to show, right? Because in Boolean circuits, we can count the number of Boolean circuits of size S. But if you have S gates, for each gate you have to specify the operation on the gate and the two children of the gate. So if you do the calculation, you figure out quite easily that there are something like S to the S Boolean circuits of size S. Now, the problem with this approach for arithmetic circuits is that there are constants from the field, and the field can be infinite. So even a circuit, the number of circuits of size 2 is infinite, or size 1, right? So you cannot just do counting argument, you have to replace counting with some other argument. And and the very simple solution is, instead of counting, just use dimension arguments. So basically what we are going to show is that we can write a universal circuit such that every circuit of size S will be a projection of that circuit. Okay, so we will have a universal circuit that has something like S square variables in it, and every polynomial that is computed by a small circuit is a projection of the polynomial that is computed by that circuit. And then simple dimension arguments will tell us that the variety of polynomials computed by small circuits is not large. So that is going to be the program, okay? So let's start by defining what is a universal circuit. So I will not give all the details, I'll just give enough information so you can complete the details. So basically, we want to describe any size S circuit, okay? So how do circuits of size S look like? Well, they have S vertices, so the depth is also at most S, right? So you can imagine having layers with S vertices in each layer, and having at most S layers, right? Now, in a circuit, you can also imagine that we order the vertices in such a way that a vertex always computes a function of two guys from lower layers, right? So to each vertex here, you have to specify two children and to say what's the operation on those children, right? So basically what we need is some gadget that allows us to compute any polynomial on two variables, or not any polynomial, either the addition of any two variables or the product of any two variables. So basically what we can do, and this is very wasteful, so for every two gates, I don't know, V, or let's call this V. So let's say for any U and W here, we can have something like, this gate will compute something like Z, I don't know, plus UW times U plus W plus Z times UW, U times W. And then it's going to be summation over all UW on layers below V. And now notice that by setting those Z's to zeros and ones, I can decide what is the operation in the gate. And in fact, we can actually do more, because if you want to take linear combinations, right? So you can add a couple of more variables here, right? Like, I don't know, Y, right? Y, U, Z, W, and then Y prime, U, Z, W, right? So if every gate will compute that function, then by substituting zeros and ones to the Z's and constant to the Y primes, we basically can get any gate that we want here, right? And so it should be clear that any size S circuit can be obtained by setting values to Z and the Y's, right? So okay, so this, let's call this the universal circuit for size S. Okay, there are many ways to define. This is maybe a wasteful way, but it's some way to do it. So how many constants, how many new variables did we introduce in that process? Well, for every gate, we introduce something like, I guess, S squared new variables, right? Because for every per unit W. So the total number of Z and Y vars is something like O of S cubed. Right? So that's the total.
Why do you actually need the layers?
Probably I don't. I just, when I prepared it, that's what I did. And, and it's not needed. Yeah, we don't need the layers. Sorry, so we just need S gates.
What's the degree issue?
There's also the degree issue, but
One of the things is you want the universal circuit to be of low degree.
of low degree. Yeah, so this will be of degree at most. The degree can be exponential, right?
So usually you
Yes, okay, right. So we actually need not S, but rather D layers, or log D layers, I guess. O of log D layers, because every circuit can be, okay. So, no, O of log D. Okay, sorry. So thanks, Michael, for the comment. Yes, that's why we have Michael here. One of the reasons that we have Michael here. Okay, so thanks very much. So yesterday, when I presented the depth reduction, so actually maybe log squared D layers, I guess. Well, okay, log, yeah, okay, yes, and then we can have, okay. So let me, okay, I usually wave my hands too much and then I get corrected. Okay, so, good. So let me do it, thanks. So I'll do it again. So yesterday we saw depth reduction, and the depth reduction proof showed that any size S circuit can be parallelized to get a circuit. Okay, so Ramprasad mentioned it's a circuit of depth log S times log of the degree of the output polynomial, but the structure of the circuit was that there were log S or log degree alternating layers with plus and times gate, where times gate had fan-in 5 and plus gates had arbitrary fan-in. So basically what we need is that V should either compute some arbitrary function of its children, arbitrary linear combination of its children, right, times, I don't know, ZV, I guess, or some product gate. Okay, so each vertex, right, so that's a correction to what I said earlier. Each vertex either computes some linear combination of gates that were computed beforehand, or it computes some product gate. And in fact, the layers are also needed. I mean, we can also demand that the vertex at layer I computes a polynomial of degree exactly I. I mean, I don't want to get into all the fine details, but I think it should be clear what we do. So a vertex either computes an arbitrary linear function or some product gate, right? So setting the z's to 0s and 1, you can either fix this to 1 and the others to 0, so you get an arbitrary linear combination, or you can fix this to 0 and one of those guys to 1. And now when we have log D layers, so we know that the degree never goes above some polynomial in D, and that's it. Okay, so that's a universal circuit, and again, the number of, so for each V we have like SYs and SZs, so again, so now the total number is actually, it's even better, right? It's S squared. Right, that's what we get. No, sorry, we have S log D, so it's like O tilde of S squared, I guess. Many new variables, right? The number of, if you just count the number of variables that we introduced for every vertex, it's O of S, and there are log D levels, each log D layers, each layer is S gate, so it's roughly that number of new variables. So what does it mean? Now think about the, okay, so that's the universal circuit. So now you can think about the polynomial that you get at the end. Let's look at its coefficients. What are going to be the coefficient of the computed polynomial? Each coefficient is going to be some polynomial in those new variables, in those z's and y's. Right? We're going to compute some polynomial, so the output is in, okay, let's call it like this. It's some polynomial with coefficients y and z, and it's a polynomial in the x variables. Right? Let me just write it like that. That's the ring from where the coefficients are taken. So, and any substitution to the y and z give you some polynomial that can be computed by size, or, sorry, any size a circuit, for any size a circuit, there is some assignment that computes such that the output polynomial is a polynomial computed by that circuit. Good. So now I want to understand what's the dimension of the variety that we have here. And basically this dimension is determined by the number of y and z variables. Right? You can think about the polynomial as a vector of coefficients. So we have a mapping from that many variables to, I don't know, to the coefficient of all the degree d polynomials. So we have some mapping gamma from, I don't know, f to the O of s squared to what? To f to what? So if we have a degree d polynomial, so the number of coefficients is roughly n plus d choose d. And that mapping takes the y's and z's and outputs the coefficient of each monomial. Right? So the polynomials that can be computed by size s circuits are in the image of that map. Right? Their coefficients are in the image of that map. So to show a lower bound, it's just we have to prove that there exists a polynomial whose coefficient vector is not in the image of that map. And this will tell us that it cannot be computed by size S circuits. Not necessarily. Maybe there's +1 or -1 or whatever. Yeah, it's roughly. Yeah, I guess. Maybe. No, I think that's for non-homogeneous, right? For homogeneous, it will be -1.
That's correct. For non-homogeneous.
This is non-homogeneous. Yeah. Okay, so yeah, then that's O tilde, I guess. So yeah, so just do counting argument now, right? If we have that O tilde of S squared is smaller than that number, then we know that there exist degree d polynomials in n variables that cannot be computed by size S circuits, right? And that's give a lower bound of roughly square root of that number. Okay? And this is also tight because every polynomial can be computed by square root of that number. Okay. There are n variables. I didn't specify. I mean, you can assume that the bottom layer is x1 to xn. Yes. Yeah. Here in the universal circuit, you also have x1 up to xn. Okay. I mean, the variables y's and z, they specify how the circuit is wired and what are the constants in the circuit. Okay, that's what they specify. Okay, good. Okay. Right, so this is just the general counting argument. Sorry? Right. So, but the total number of variables, you just count them. It's like, it's S squared. Z and Y are, they're external variables. They're not part of the computation. They just, to get, for every circuit of size S, there exists an assignment to the Z and Y variables such that the polynomial that is computed by that circuit equals the polynomial that is computed by the size S circuit.
Yeah, I see, but I don't see here. Oh, Y.
Okay, good. So this shows that there exists, that if S is not too large, then there exist polynomials that cannot be computed by size S circuits.
Is S squared necessary?
I think it's necessary. Yeah, I think you can compute everything with square root of that, or at least that number of multiplications, right? Sorry?
It's multiplications.
Yeah, okay. So, yeah, it's unnecessary. It can be O of S, S, yeah, you can save the square, I guess. But if you, okay, but, yeah. But you can do with square root. If you only count multiplications, you can do with square root of that number, for example. But that's, okay. Now, another question we can ask is about what's the relative size of a size S circuit versus size S cube circuit, for example. So here's another theorem that, I don't know, theorem, okay, it's like the size S is contained not equal in size, let's say S square or maybe, okay, it's 2 plus epsilon. So it's probably true also for S to the 1 plus epsilon, or S times polylog when the polylog is large enough. But I'll just say a very simple argument. What Michael is going to show later today is that he's going to give something that's called the heating set for arithmetic circuits. And the heating set is a set of inputs such that a heating set for size S is a set of inputs such that a size S circuit that computes a non-zero polynomial cannot vanish on all of those inputs. Okay, Michael will define those notions. Yes, so is a proof. Okay, maybe Michael will say.
I think it's, the same argument if you scale it down is set n to be like.
Yeah, that argument you mean, or which argument?
Yeah, the one you just did.
But okay, I don't want to. There's a issue of just showing that the variety is not degenerate, right? Or that
Basically, like, you know, take all polynomials on like polylog s variables.
right.
Right. If you have a size s circuit, just restrict to like zero out everything else, those coefficients, and just pay attention to this. And then
Okay, so
insane the number of.
okay, so basically, okay, so we want to say 1 plus epsilon, right? Oh, doesn't matter. Anyway, sorry. Okay, we shouldn't argue during this thing, but at least. So here's one proof that you'll see today. There exists a set H of size roughly of S squared, such that if C is of size S, and C computes a non-zero F, then there exists some, I don't know, alpha in C in H such that F of alpha is non-zero. Okay, so that's this is something that Michael is going to show. It's again some dimension argument, counting argument. And the point is that in size 2 plus epsilon, you can construct a circuit that computes a non-zero polynomial that vanishes on all points in H. So this polynomial is going to be non-zero. It vanishes on all of H. So it means that it cannot be computed by size S circuits. Okay, so that's roughly an argument, and there are probably many ways to prove that. But yeah. Okay, so these were just. So yesterday we spoke about VP or VQP, and so certainly this implies that. So as a corollary, of course, VP is not VQP, right? So yesterday when, but okay, so this tells us that yes, the two classes are not the same. But something that is still open, also open here, is to find an explicit polynomial that belongs to VQP and not to VP, or an explicit polynomial that can be computed in size S cube and not in size S, or any polynomial that cannot be computed in size S, not necessarily in S cube. Okay, so counting arguments gives us lower bounds, but we don't have an explicit example of our polynomials. Yes? So, sorry? VQP is quasi-polynomial. Yeah, it's not quantum. Yeah.
I mean, the projection is that we define yesterday as such that it's possible that wouldn't the determinant being complete for VQP qualify as one of those?
Yeah, but it has a VP circuit, right? I mean, it has a polynomial size circuit. Yes. Yes. I don't know. Like natural proof argument, right? I mean, it's Boolean circuit, but that's what makes it so difficult, right? I mean, so we don't have a natural proof argument for arithmetic circuits, but I think the intuition is the same. Using natural arguments, I mean, in the Boolean case, it doesn't take us far, right? So I think that's, I mean, so, again, sorry? The natural argument is Rasborov Rudish. Yes. Okay, so that was a counting argument. Okay, so what I want to show next is a concrete lower bound that we have, a superlinear lower bound. And so, okay, let me just state the theorem. I think that Ramprasad mentioned it yesterday, is that the theorem is of Bauer and Strassen. And it says the following, that summation xin, if you look at, let's say xid. So if you just take the sum of the trace, the degree d trace, then requires circuits of size omega of d log n. Sorry? It's a log d, sorry, n log d. Thanks. Yeah, so, and clearly this is also an upper bound, right? Because you can just compute the iterative squaring that takes log d, and you do it for each variable, and you sum them up together. Yes? Okay. All right, so let's prove this next. And Okay, so how does the proof look like? So the first step of the proof is, as Prasad said, is to use Bauer-Strassen theorem. What does Bauer-Strassen theorem tells us? That's what Prasad proved today, that if we can compute a polynomial in size S circuit, then in size 5S we can compute all its partial derivatives together. Right? So to show a lower bound for one polynomial, it's enough to show a lower bound for n polynomials. Right? So it's enough to show lower bound for the polynomial xi to the d minus 1 up to xn to the d minus 1. Okay? Because these are all the first order partial derivatives of that polynomial, up to constants, right? We don't care about the constant. Okay, so basically I want to show that any arithmetic circuit that computes those n polynomials simultaneously must have size at least that much. And this is not a trivial task because, for example, for Boolean circuits, even if we allow n outputs, we don't have superlinear lower bounds. Okay, so it's really something interesting. Okay, so what is the idea of the construction of the lower bound proof? So the basic intuition is that okay, and let's speak about and let's see fan into. Okay, so for the sake of the argument, it will be helpful to think about circuits with fan in 2. As you said, it's up to, I mean, it doesn't really matter. So the idea is that such circuits only compute local operations, right? They only operate on, I mean, they always compute, I mean, right? If you look at the circuit and you think about what happens in a gate, so what happens, it's always either a linear function, right? Because you compute the sum of two things, or it's like a degree 2 operation because it multiplies two things. So in some sense, we apply many operations, but they're like S operations, if S is the size, but they're all of low degree. And when this is the case, it gives some weakness of the circuit. So let's do it more formally. So for each gate, introduce, okay, let yv be a new variable. Okay, so we introduce a new variable, one for each gate. And now I want to somehow capture the computation with those variables. So for example, I'm going to introduce a set of equations such that, okay, let me write it and then it will be clear. So let's say that we have a gate V and two children U and W. So if V is U times W, we will introduce the equation that what we computed V should be equal to U, right? And if V is U plus W, then we'll have YV minus 0. And of course, if, let's say, if V is just some variable, I don't know, then we'll have YV minus XI. And if V is a constant, some alpha in F, we'll have YV minus alpha equals 0. Right? So what happens here? So just notice that take any solution to that system of equations. What does it mean, a solution? It means you should find values take a value for the x variables and a value for the y variables, such that all those equations are satisfied. Yeah, and let's call this gate O, the output gate. So if all the equations are satisfied, then I claim that the YO must be equal to f of x. Right? If you find, I mean, take any substitution, any input that satisfies all the set of equations for all gates V in the circuit, then the output gate equals that polynomial. And you can just prove it by induction, right? That every gate computes the polynomial that is computed in the circuit. Right? Great. Yes, or Y out, yeah, Fi. Thanks. Yeah, it should have, it's 01 up to 01. Thanks. Right. Okay? Right, thanks. Okay, great. So it means that, so again, we are going to use some dimension arguments, basically saying that, Okay, now we can also look at the equation of, let's say, y or I equals minus 1 equals 0. Okay, let's also do this equation. So what do we have? We introduce another, I mean, forget about this. This was just to understand what's going on, okay? So let's also introduce that equation. So what would be the set of solutions? The set of solutions to that system of equations is exactly all the inputs x, such that the output, all the outputs evaluate to 1 on those inputs. Right, so maybe I should write it. So this, so consider for, so we have a system. So which, okay, we can, yeah. So well, yv is, I don't know, minus yu times yw, etc. Yu equals, I don't know, yz minus y something, etc. Right? We have that, or minus. So we have the system of equations with all. And then at the end we have y(i) minus 1 equals 0. And the solutions to this system give us exactly all the inputs for which all the output gates compute the constant polynomial. They evaluate to 1. So now we can use a result from algebraic geometry called Bezout's theorem that bounds the number of inputs, the number of solutions to such a system. Okay, so Bezout's theorem tells us the following, that so let's say you work over C or over C, let's say, but it's not just C, but let's state it over C, that if we have f1 of x up to f r of x is a system of polynomials, and the degree of fi is, I don't know, say di, and the number of solutions such that, okay, so we look at the solution to the system, so all fi is evaluated to 0 simultaneously. So if this number is finite, okay, then this number, it is at most product of I of di. Okay? If it's not infinite, then it's small. Okay? It can be infinite, for example, if all the polynomials have some common factor, because then, etc. But if this number is finite, then it is bounded by the product of the degrees. Okay, so let's go back to our system of equations. So assume that we compute polynomials f1 up to fn such that the number of solutions to this system is finite. Okay? How large can it be? So if you look at what happens here, we either have equations of degree 1 or equations of degree 2. Right? Never get higher degree equations. And how many equations of degree 2 do we have? Number of multiplication gates, right? Because these are the only gates introducing degree 2. So what is the corollary? So, okay.
So why is the number of varieties finite?
It's, I mean, if it's finite, it's this. I didn't say it's finite, okay? You know, maybe let's go, okay, let's continue. Remember, what we are speaking about, we are considering a very explicit set of polynomials. And we are looking at all the solutions of 1. So how many solutions are there to the equation xi to d x1 to d minus 1 equals 1 over the complex number or over any field? There are at most d minus 1 solutions, and actually there are exactly d minus 1 solutions, right? Because if you look at the algebraic closure. So we know that if we look at what we did, I mean, we wanted this output to be equal to 1, that output to be equal to 1, that output to be equal to 1. So the total number of solutions is what? Is like d minus 1 to the n, right? Because every one of them is d minus 1 to the n. So here's a corollary of what we wrote. So corollary. If C computes x1 to the d minus 1 to xn to the d minus 1, then 2 to the number of multiplication gates, right, should be at least, because this is an upper bound. Actually, it is exactly if you count correctly, but never mind. It's an upper bound. It should be at least the number of solutions, which is d minus 1 to the n. And that's it, right? That's the lower bound. Okay? So, wait, what's the time?
How complicated is it to prove the Zoot theorem?
It's a book. It's an undergraduate course. It's it's not very complicated. But it's not trivial also. So Nati, don't prove it now. But okay. So if the Fanin is, yes. Yes, and if the Fanin is not 2, then you just, you replace each I Fanin with a small tree, right? So it multiplies the number of edges by a factor of 2 at most. Yeah. No, if you have a large Fanin, you just build a small tree of. But the number of gates you say grows. Yeah, but that's lower bound on the edges. Yeah.
So in this case, you want to compute the n functions, and the first function only depends on x1, the second one. In other cases in which you can gain by mixing them?
No, what's the, there's a bottleneck here, and the bottleneck is, you can never prove anything above d log n using this, or n log d using this technique.
No, I'm saying, is there any hope of proving the lower bound using the following approach? If you just want to compute x1 to the d minus 1, then it's easy to show that you need the log d.
Right, but you don't, no, because you can mix, right? For example, well, okay, it's tight, right? The lower bound is tight. But I can give you a circuit that mixes and has the same thing. Okay, so, I think it's not a unique circuit for that question. And the other circuits use mixing, but it doesn't tell because you have a tight result. But you want to start from any circuit and say that you can unmix the thing. That's arguments are usually very difficult to do, right? Yes, for example, the symmetric polynomials, if you want to compute the n symmetric polynomials, elementary symmetric polynomials. Basically, it works for any set of n polynomials for which you get many solutions, but finitely many. Yes, one polynomial, that's a polynomial, right?
Yes. So, how general is it?
I'm not sure. So we don't get anything above n log d. And the only techniques we know how to prove such lower bounds is to start from one polynomial whose partial derivatives have many solutions. And that's the, is that what you asked? Okay, yeah. So yeah, we lack techniques for general circuits, and that's the only technique we have. Yeah, so this also holds for, for very large, you have to be careful because of the derivative. It can become 0. So certainly if the characteristic is large enough, that's good. What happens over other fields? So if the characteristic of the field is large enough, then everything still holds because the derivative is not 0. For other characteristics, I don't remember. Do you remember it?
You have to make some.
No, you have to. Then you have, sorry? No, you compute the polynomial, not the function, right? X to the d is not x. No, so I don't see it, sorry. Yes. So, but I don't, do you remember, does it, I don't know if you have techniques for small characteristic. Yeah, okay, no, so not for that polynomial, but for other polynomials. Right, so the problem with that polynomial is that if you take partial derivatives, I mean, I didn't write the D, it will be 0. But you can take other polynomials, like the elementary multilinear polynomials, and that will be fine. Okay, so what Nate asks is what happens over a small characteristic, positive characteristic, and then you just need multilinear polynomials rather than such polynomials. Yeah, thanks, Nate. No, it holds for the algebraic closure. It is. I just wrote C because of the partial derivatives issues. That's it. I mean, that's the simplest example because it's very easy to see the number of solutions here is like d minus 1 to the n. But if these were the elementary symmetric polynomials, then still, I mean, you get all possible, you have enough solutions. Okay, good. So what's done? Okay, so, yeah, and maybe here I forgot to say something. So when we spoke about the general lower bound, we did this dimension argument and said there exists a hard polynomial just because the image of the map is not everything. But what I forgot to say is that we can also prove that there exists a hard polynomial with 0, 1 coefficients. Right? So this dimension argument just says that if this number is more than that number, then there exists a hard polynomial, but we don't know anything about its coefficients. However, one can prove, and we are not going to do that, that there also exist 0, 1 polynomials with 0, 1 coefficients that are not in the image of that variety. Because basically you can bound the size of the intersection of that variety with a large Boolean cube. So we'll not get into it, but that's just, it's also a question of how nice the coefficients are, and you can get, there are polynomials with 0, 1 coefficients. Yeah. Yeah, and maybe I'll also mention that, so this is a general lower bound for circuits, and what about formulas? So I will not show this lower bound, I'll just state it. So there exists, an omega n squared lower bound for formulas due to Kalokrotti. And and that's the best lower bound that we have for formulas. So I think for determinant you get n cubed, but you have n square variables. Which polynomials give n square? I don't know. You can design some polynomial that will do it. Do you remember off the top of your mind?
It's something like summation x. It's a sum over I, xi times the sum over j y bar j.
Summation xi, summation over j. Y power j. No, but that's degree 1, no? Okay, there has to be something. Okay, I mean, the idea is that you want the partial derivatives to be algebraically independent, and then you get, it's around omega n squared. So,
Back to your previous comment on 0, 1 coefficients. Do you know other simple interface things which are hard? I don't know, multilinear?
Yes, multilinear 0, 1 coefficients. Yes. Yeah. Okay, so this is the lower bound we have for formulas. I will not go into I will not say anything about the proof, but yeah, we should do better than that. Okay, so that's what we know for the general model of circuits and formulas. So, so if I think the precise assessment should be that if this is more than that, I don't know whether it's really, I think it's the same parameter, and there exists a multilinear polynomial with 0, 1 coefficient. Then by sub-additivity and the fact that the building block is a small measure, a polynomial that is computed by a small formula as a small measure according to mu. Sorry? Yeah, so so that's why I said the building block. Building block will be the entire product, say. Okay, or some. It depends. At that level of discussion, everything is legit. But okay, so a polynomial that is computed by such a circuit will have a small measure, And then the only task of proving lower bounds, okay, so the task is coming with such a mu, and then finding a polynomial that has large mu. And this is always kind of easy, because like a generic polynomial is large mu, which doesn't say much, but this is usually not the difficult part. The difficult part is coming with a mu that's also that enables us to show these things. Okay, and that Ram Prasad will do next. And maybe one last thing, because it's something that we mentioned a lot yesterday, but we never defined it. Let me just finish with a definition, clear definition of the low depth complexity classes that we discuss. Because we keep mentioning depth 3 circuits, depth 4 circuits, but so depth 3 circuit, right? It has 3 layers, right? But somehow the definition of arithmetic circuit, we have to slightly change it, because we want to allow the bottom layer not just to compute sums of variables, but to compute arbitrary linear combination of variables. So for this, we should have added in principle another layer of product gates that takes a variable and a constant and multiply them. But when we speak about small depth circuits, what we'll do is we'll just allow linear, when you take a sum, we'll just allow any linear combination rather than sum of variables. Okay? So basically, depth 3 circuit of that form of plus, of times of plus, is called sigma pi sigma circuit. And it computes a polynomial of the form summation of products. So let's call this S. And then this, the ith gate, will have degree di. And then Lij's, where the Lij's are arbitrary linear functions. Okay? So this is just, if it bothered anyone, so we allow arbitrary linear combinations when we speak about shallow circuits. Okay, we don't charge you for multiplying with constants. Yeah, the product gates don't need constants, and so if you have a constant times 0, you can just somehow push it down, right? So it doesn't matter. And similarly, when we say sigma pi, so that level of products compute monomials. Then we allow you to take arbitrary linear combinations of those monomials, and then multiply them, and then, okay? So when we say sigma pi sigma, we allow those arbitrary linear combinations. When we speak about those, we allow arbitrary linear combination of monomials, etc. This is just some. Okay, let's take a break, and then Ram Prasad will.